So now that we've seen Lagrange method, let's take another look at minimum variance portfolios and just see what we have to do to solve one of these optimization problems. So a minimum variance portfolio, this was the quantity I was calling risk, which is just the variance of my portfolio. And I want to minimize my risk, so I want to minimize the variance, subject to two conditions. One, that I hit my target rate of return. And two, just this is sort of a more realistic, like there's no way around this condition, that my money in my portfolio has to all be sort of used up. So the proportions of my portfolio, my weights, have to all sum up to 1. So to set this up for Lagrange method, the objective function, the f, the thing that I'm trying to minimize or maximize, is going to be the variance, so W transpose sigma W. And the constraints, so G is going to be a function of this weights vector, so the weights of my portfolio. It's a vector-valued function with two pieces. The first one is just this condition. So here I haven't written them equal to 0. So when I write this out in the g of x, I have to, oh, I guess I swapped them too, but that won't make any difference. So instead of saying that the expected return of the portfolio should be equal to my target expected return, I'm going to say the expected return of my portfolio minus my target expected return has to be equal to 0, and that the sum of the weights minus 1 has to be equal to 0. And then I'll check my necessary condition. So if I take the gradient of this, I'm just going to end up with mu transpose as the first row, and the second row being all 1. And so the only way I could get into trouble is if I managed to pick n assets that all had exactly the same expected return. So if 1, the vector 1, so 1 in every element, that's proportional to any vector that has the same number for every element. So as long as I have at least 2 distinct expected returns among my assets, then this matrix is going to be full rank. It's going to have 2 pivots for 2 rows. And I need an intermediate result, which is something called the derivative of a quadratic form. So I'm going to let A be a symmetric matrix. So this is just a 2 by 2 example. So I have diagonal entries A and C, and then the off-diagonal elements, they have to match. So for a 2 by 2 case, there's only one off-diagonal element, B, and so I guess it's 2, but they have to be the same. So the 1, 2, and the 2, 1 element are the same value. And then I'll define f of x to be equal to, so x is going to be a vector of 2 elements, x transpose ax. And when I do that arithmetic, what I end up with is a x1 squared plus 2b x1 x2 plus c x2 squared. If I take the derivative of that, so the partial derivatives of this, I end up getting 2x transpose A. So you can kind of see what's, it makes sense because this x transpose AX, this is sort of the matrix equivalent of just what a single variable function would have as AX squared. If I take the derivative of a function that's equal to AX squared, I get 2AX. And so that's pretty much what I've got here, except I just have to respect the order of operations so that I get the right answer that I want to. So the gradient has to be a row vector. So I need to do this as x transpose A so that the answer here is going to be a row vector. And then I pick up this factor of 2 because it's sort of the same thing as taking a derivative of x squared. And it turns out that in general, if A is an n by n symmetric matrix, so that's what makes this thing a quadratic form, is if I write this here. So x is my vector has my variables in it, x1 up to xn. And A is a symmetric matrix. Then this thing here is called a quadratic form. So the derivative of a quadratic form, so the gradient of the corresponding function here, you can just write that as 2x transpose A. So it works for the 2 by 2 case like this, and if you actually did the same thing but for larger cases, 3 by 3 or n by n, you would be doing a whole lot of calculations, but in the end, you're always going to get 2x transpose A. So, okay. So now let's look at the Lagrangian I have for my minimum variance problem. So I put the variance here. So this is the little f. Then I have lambda 1 times constraint 1 plus lambda 2 times constraint 2. And now I want to take the gradient of the Lagrangian. So I can do this again, doing sort of the x part first and then the lambda part second. So what I end up with is the gradient of the objective function, so the little f. And so that's, I've just said, I've just mentioned how I can take the derivative of this quadratic form. So that's 2w transpose sigma. And then I'm going to have lambda 1 times the gradient of g. So the gradient of g is going to just be, if I look at the gradient here, will just be a vector of 1s. So it's 1 times w, and I'm taking the derivatives with respect to each of these w's. So each time only one of those terms is going to pop out, and it's always going to be a 1. And then similarly, when I do the same thing here, oh, and I guess this 1 is constant. This mu p is constant, so they're going to disappear when I take derivatives. And the same thing's going to happen here. When I take the gradient here, I'm just going to get mu 1, mu 2, mu 3 in a row, because everything else I'm taking a partial derivative with respect to a different variable. So I can write that just as lambda 1 times E transpose plus lambda 2 times mu transpose. And then the partial derivatives with respect to the lambda here, they're just going to be my constraints again. So I end up with E transpose W minus 1 and mu transpose W minus mu P. And so I guess we should check that all of the dimensions work out here. So W transpose, W is a column vector with n elements in it. And this is an n by n matrix. So when I take W transpose, that has dimensions 1 by n. Sigma has dimensions n by n. So when I do that product, I'm going to get 1 by n. E transpose, this is this column vector of n ones. So when I take the transpose of that, I'm going to get a vector here that has, it's a row vector with n elements. And similarly, mu transpose is also going to be a row vector with n elements. So I can do this sum, and I end up with a row vector with n elements. And then these are each scalar values. So I have n elements here, and then I have 2 lambdas, so I end up with 2 more. So m more terms here, but in this particular case, m is equal to 2. And I need to find values now of w, lambda 1, and lambda 2 that are going to make this equal to 0. And so it turns out you can write that problem down just as solving a linear system. So I have 2 sigma, so that's here 2 sigma times w. So this is just the transpose of this. So it's kind of more convenient to work with this as a column vector when I want to solve it. Lambda 1 times E transpose. So that's going to be, if I just take the transpose of that, lambda 1's a constant. So that'll just become E. And then lambda 2 times mu transpose. So I end up with mu here. And now if I do the dot product of this row and this column, I end up with 2 sigma w, E plus E lambda 1 plus mu lambda 2, which is just the transpose of this here. So if I can make this thing equal to 0, then I'm also making this thing equal to 0. Then I need E transpose W has to equal 1. So here I have E transpose times W plus 0 times lambda 1 plus 0 times lambda 2 equals 1. So that gets me this constraint here. And then mu transpose times W plus 0 times lambda 1 plus 0 times lambda 2 equals mu p. So that gets me this constraint here. So it turns out in the case of this minimum variance portfolio, I'm able to find there's going to just be one critical point because this is a linear system. And I'm able to find that just by solving this AX equals B problem that we worked on in the linear algebra section of the lectures. And so that's it for the lecture today. There's still one more quiz, but I just wanted to mention some further reading. So there is also a reasonably complicated second-order condition for whether a point you find using Lagrange multipliers is a maximum or a minimum. And that's described in the course textbook. So Theorem 9.2 and Corollary 9.1.